Okay, thank you, Maria, for the introduction. I'm here to present the work of Konstantinos, who's my student. He did most of it. I supervise it, but unfortunately he cannot be here today because he works in Malta. It's a bit far away. And unfortunately the conference didn't support hybrid participation. So I'll try my best to convey the fundamentals of the work. And of course, if you are interested in this type of thing, if you want the source code, if you want to ask about technical details, then please feel free to contact either me or Konstantinos directly, and would be more than happy to share further information with you. So, what's our motivation for this work? The work relates around the concept of controlled environments in industrial situations. So if you think about like a nuclear plant or a transport center, or even a marine vessel. Okay, these are industrial installations, right, that need dedicated control rooms. So typically for this type of thing, you need a huge room, lots of displays, lots of workstations here and there, and coordinating between all the information that you need to get from the various displays or the various areas of information intake. Can be quite difficult. So our idea was to try and replicate this controlled room situation, but do it in VR, because VR allows you to basically not be physically present at the space. So you can remotely monitor another industrial installation. It allows you to do things like, for example, dynamically bring bits of information together, whereas in physicality, they would be separated and be dispersed all around the room. So be quite difficult to monitor all of them at the same time. You can use a single device, which would be your head-mounted display, for multiple control scenarios. Like, for example, you could be a marine engineer sitting in the office in Athens and then monitoring a ship that is in Korea, another ship that's in South Africa, another ship that's in America, whatever. You don't need to do anything. So, and of course, these are different environments because they're different ships. So this is the motivation behind all of this. And within this context, within this problem space, we try to look at the specific sub-problem, because obviously there's a lot more of this, but we look at a specific sub-problem of information overload. So you have all these instruments providing information, or these displays providing information to you. Something goes wrong, and you need to quickly locate the source of that problem. Okay, you need to quickly locate what instrument is the one that raised the alert. And of course, get an understanding of the situation, then act accordingly to rectify it if you can. Okay. So one question, how to locate important information, i.e. alerts, quickly and accurately. And secondly, how to divert users' attention to these alert raising instruments without providing additional visual clutter on top of an already cluttered information space, which is the control room. And the approach we took was very subtle. I'm surprised that this even worked at all, but I did. So the approach was very subtle. We tried two modalities. Said, okay, let's not use the visual channel, or at least not use it as much, using a low fidelity sort of way. So one of our approaches was to have directional lighting. So if you can imagine a kind of siren type thing attached to each instrument, and the siren rotates. So you don't really see the siren itself. The siren is invisible, but you see the light reflected on the panel surfaces behind it, okay, and all around the room. So if you can imagine a siren being placed in the middle of the room, and if you're all looking at me, nobody can see the siren, but you can see the light sort of moving around, and you know that something's going on. And of course, we gave this directionality. So if the light moves that way, it means the alerting instrument is somewhere along that trajectory. So you need to follow that trajectory to locate it. If it's in the other way around, you follow the other way around with your eyes and you locate. So that was one way of dealing with the problem. The second one was using spatial audio, so 3D audio. So again, audio sources connected to all the instruments, and every time something went wrong, you get a buzz, a beep rather, and it's directionalized, so you can kind of roughly guess, okay, the sound's coming from over there, so I need to look at the instrument over there. And of course, we did a combination of both. to see if that works any better. Our control environment replicated a complex control situation with a room extending 360 degrees around the user. So you're sat at the middle of the room and you've got information all around you. The alerts raise instruments. What you have to do is you have to find the instrument that raised the alert, and then correspondingly press one of the virtual buttons on the console around you where you're sitting with your virtual hand. So you have hand tracking. You see a voltage meter is causing trouble. You find the voltage. You see that that's what it is. You find the voltage meter button, which is directly beneath it, and you press it. Okay, that's how you dismiss an alert. So we did an experiment for this to see which way of alerting works best. Pre-experiment, we did some benchmark tests to make sure that all the participants that we employed were fit for purpose. So no outliers in terms of cognitive abilities or visual abilities or reaction time and things like that. So this was a very simple desktop-based experiment, not in VR. Okay. And we did a demographic questionnaire, and the main experiment was a within subject design with 3 conditions: audio, light, and mixed. We had 10 alerts per modality for each participant with a balanced Latin square to avoid learning effects, and we gave them a NASA TLX at the end of each condition as well. So to satisfy the balanced Latin square, of course, we needed a multiple of 6. So we recruited 24 participants. Nine of them were female. That's a study kind of adequately powered to detect large size effects. So we were hopeful we would find large size effects. Just a few words about participants. Most of them, as you can see, didn't have any previous experience with VR. Only 9 of them had some experience of VR use, but only 3 were owners of VR equipment and use it regularly. However, they were all around the same age. And the ones that we selected, because we had to reject a few, were within 1 standard deviation, the sample mean, and all the benchmark tests. So we consider them a homogeneous group. So time for the results. To sum it up, audio alerts are the best, right? I mean, the mean reaction time was the lowest for spatialized audio. Use of lighting and spatialized audio together gave comparable results, but again, the difference between audio alone and that mixed type was statistically significant. So we can quickly conclude that. Something I forgot to mention earlier is that our alerts were also issued at levels of priority. So we had high priority, middle priority, and low priority alerts, which were either color coded in the lighting display or audio coded with modulation of the intervals between the buzzes, right? So we found this effect was true across all modality types. And additionally, we also noticed that participants consistently dismissed high priority alerts much quicker than low priority alerts. So this at least gave us some confidence that they took the experiment seriously and they weren't just playing about. About subjective results from the NASA TLX, we found that mixed modalities seem to be the most mentally challenging, according to participants' subjective reporting, without any distinct performance advantage, of course, because we saw the alerts were the faster ones. Participants felt that localization was mentally more challenging with the audio modality compared to visual, but not audio versus mixed. Temporal demand higher with audio, which is kind of funny because in reality they took the shortest time to respond to these alerts. So okay, this is why you have subjective and objective data in every study as well. Finally, subjective performance was best with audio and mixed versus virtual reality, which at least confirms our findings, although they thought they were slower with it. And some good news, frustration was low overall for all modalities. The lowest frustration was with visual modality, so it means that yes, they did. In the end, I think the results interpretation is that they did work harder with audio, but they were much more successful with it. And thankfully, it doesn't seem to be that taxing. So probably that's the way to go if you want to do unobtrusive alerting in VR. Okay. So just to sum up, ambient layering in such control environments seems to be a positive, good way forward. And I think this becomes apparent if we contrast this with some previous work that we did, where we provide very high fidelity visual cues to participants in a similar control situation. So directional arrows and lights and the names of the alerts and all that. This time, just using the spatial audio, the alert time was 3 times faster than the overloading of the visual channel with additional information. But of course, the work has many limitations. Of course, this was an artificial environment. There was no real pressure to press the button or the nuclear reactor would explode. Okay. We need repeated studies to show performance curves and see if perhaps the other modalities maybe surpass audio over time. We don't know that. Of course, we've had single use scenarios only here. And of course, one of the big advantages with VR is that you're not just alone. You can collaborate with other participants within the same VR space. And this is something that needs to be explored, the common perception of modalities and their directionality. What else am I forgetting? Oh, yes, of course. And of course, we had a static configuration of the control room. So I imagine that even with a longitudinal study, if we do see an improvement, part of that improvement will be due to familiarization with the layout of the room and the layout of the instruments. So we'd like to mix it up a little bit and try and see if we can dynamically adapt the room for certain situations, dynamically move some instruments together, and so they would be in a place that the user wouldn't normally expect it, and see how that might affect the performance of the alerting systems. Okay, that's it from me. I'm not going to take more of your time. So if you have any questions, I'll be happy to take them. I'm also around the whole conference day tomorrow. And if you're here for Mobile HCI on Friday as well, feel free to come and see me. Okay.
Thank you. The usual suspect has a question. Anyone else? And then I'll move to Professor Avouris. Okay. So Christos, Professor Avouris can go first, and then Christos, and then, okay. Time for it.
Okay, thank you, Andrea. This is also, and it's interesting, the both talks come from the same group this morning, and they're both very high standard in terms of experimental design, motivation, setting up the problem, etc. So well done, and especially because people know Andreas is running a major international conference at the same time, presenting this very good research. Congratulations, really amazing.
Thank you for the
Now,
comment.
just a question. The problem you're looking at is really very important, very interesting. And I just wonder you covered some of it on the limitations, on the ecological validity of your setting up. Like, I'll give you some examples. One, you'd call it, is a social context, a control room. There is more than one person normally. So and they communicate, etc. Second issue, what is the mental model of the people in the control room? How aware are they of the process they are monitoring? Are they knowing? Do they know the usual suspects, just to use your word, of possible causes of failures? So the interpretation of what they receive, or is more Pavlovian, I just see this light or auditory and just press.
Okay.
That's the second question. And the third one is, I forgot now. The third one, in real situations, usually, and we know 3 Mile Island and lots of other cases in history, is that what is called common cause effect. One fault in a complex process creates a sequence of alarms in the control room. And that creates mental confusion because you don't know what's the main effect and what are the subsequent alarms which come up. Now, in your case, it was just a single alarm.
Yes.
So these are 3 issues that perhaps in future studies would be interesting to look at in this very interesting experiment. Thank you.
To be honest with you, I don't have anything to reply to you because you're completely right. Okay, all this, all these criticisms or ideas or reflections on this work are completely Correct, and they're exactly what we had on our mind as well. So if you go to a real control room, that you have dedicated engineers for different sort of subsets of the control situation, of the control environment. They know what to do in their specific domain. They collaborate with others that are typically associated with what they do. But if something unexpected comes up, like in the 3 Mile Island situation, right? This is where the chaos emerges. There's no training for that because it's an unforeseen situation. Nobody's dealt with that before. So the information is scattered all over the place. People who need information need to establish new communication pipelines very quickly. That's not guaranteed to happen within the time frame available to solve the problem. So I think that in the future, VR control rooms will be quite good, because if you attach some sort of artificial intelligence behind it, or some other operational logic, then at least you can dynamically reconfigure what's in front of each operator, and then everybody can have all the information they need without needing to invent new ways to communicate and exchange situational awareness. But you're right, it needs to be tested. We started at the very basics, one alert, one user. It's a plausible scenario because, for example, I showed you sort of a seemingly complex control environment, but if you go to the control station of an unmanned drone, one of these long-range UAVs that fly around countries or around the world even, they are extremely complex. So, and it's one pilot only. It's not 10 pilots working together. It's one pilot dealing with their own craft. And of course, they communicate with commands, via voice. So it is a plausible, it is a realistic scenario. I could see something like that for a remote digger, a bus, a train, whatever equipment can be realistically managed with just one person. So thank you for raising these issues. I think they're very important.
For future study, but also for an application as a training environment for such contexts, because exactly what you said, you cannot train.
Actually, funnily, no. There is work that's been done for training in control rooms, which replicates an actual control room in very high fidelity within VR, and that's used for training. But this is not the idea here. The idea here is not to provide a tool that gives you a virtual environment of a physical environment that already exists. It's to provide something new altogether. Okay. But yes, good point. Okay, thank you.
Thank you. Christos, you're covered. Okay.
Just to
Yes.
really fast. Thanks a lot, Andreas. Christos from the Aristotle University. This spatial lighting, siren, and audio sound, I imagine that on a scenario with multiple alerts at the same time might be a lot harder.
Yes.
That's what I would like to expand on the third question that was.
But the way to solve this is by dynamically reconfiguring the control displays. So if you have 3 alerts coming from 3 different instruments, you're in VR. You're not bounded to the physicality of these displays. You can just move them all together and then have one siren point to all 3 instruments
To the same direction.
with the same light. Okay. So there's ways around that, but you're right. We need to explore them. We don't know how to deal with this.
Yeah. Okay. Thanks.
Okay.
Did you have a question as well? Would you like to keep it? We don't have much time, so very briefly, and then you can find Andreas, hopefully, if there is a minute that you are
You
free.
can find me. The question is if I have time to speak to you.
Okay, thank you. So I'm Theodora from University of the Aegean. I would like to say that the transgalaxies and instruments, I guess you have already the data that is being monitored, and you're trying to find a way to design instruments that are close, I imagine, to the real environment, the real place that all of this is currently being monitored. So you're trying both to find a way to visualize the data and monitor and find a way to keep the most important within reach, and trying to find the best way to provide alert to the user. Do you believe that the VR is the best technology to achieve the above? Are you using it to just visualize the data, or are you, do you believe that, are you planning on using technology on somehow acting on the real environment as well?
Okay, good questions. First of all, no, I don't believe VR is a solution to everything. I think it's a fantastic tool that offers a lot of flexibility and a lot of new ways of dealing with problems that we weren't able to deal with in the past. For me personally, I think that a very well-designed physical tactile interface is the best way to solve this type of problems. At the same time, it does have limitations that VR can overcome. And I can see VR being very useful in cases where remote presence is very much needed. For example, the shipping industry, it's very, I mean, they spend immense amounts of money flying engineers out to various countries around the world because the ship broke down, nobody knows how to fix it and so forth. So I can see something like that being very useful for them, but it's not the only way forward, okay? And it doesn't mean we'll stop doing proper design, proper interface design for physical, tactile, sort of human compatible interfaces. I'll stop here and chat later, okay? Thank you.